All right, good morning. So today is all about packet switching. So we're understanding how computers send messages from one computer to another without anything going missing. So we need to understand what packet switching is. We need to work out the role of an IP address, the Internet Protocol address in networking, and what the role of a router is and how it differs to a hub or a switch or anything like that. So we know that data is transmitted. Transmitted means both sent and received. And we know that you can send tiny files or very large files. I got this morning a package from an organization called Team Repair, and they've sent me loads of broken games consoles. And in STEM Club next week, we're going to fix them and play on them, which is quite good fun. Now, the package for all of these is small enough to come in one package because there's a limited amount of space in STEM Club. But if we had loads more, it would cost loads more. And it would have to come in multiple packets. And you're familiar with this idea. If you buy lots of stuff from Amazon, you get lots of boxes, even if it's just one order. A packet, therefore, is a smaller part of a file. As in, if you've got a very large file, multiple gigabytes, you'd have to break it into lots of packets. So, we know the analogy. A packet might be like a piece of a puzzle or a part of an order. Once you've split something into packets, you then have to reassemble it. Just like a jigsaw, you have to put the pieces back together in the same order. Imagine it's a video and you're watching this video. It would make no sense whatsoever if the end of the video suddenly started playing at the beginning. You need to know what order those video snippets are in. The same with a file. There's no point downloading a Python file if you reassemble it in the wrong order. So we need to keep track of the order. So that means the data itself is the most important bit. That's the biggest part of a packet. That's like, in this packet I've got here, that's what's inside. But that's not the only thing that you have to send. You have like the address label and the return to sender stuff. So addresses, who's sent it and where it's going to. That gets stored in either the header or the footer. Just like in Word, where you have your main page, and then at the top of the page you have your header and your footer. It's the same with a packet. But this time you've got your data and you've got your source address. You would have an IP address like 10.5.2.32 and your recipient address. So that's who's sending it. The recipient address is who it's going to. We have a sequence number, which is, sequence number. That just means order 0, order 1, order 2, order 3, order 4, order 5. And the order that you actually receive those packets in is not necessarily the order they were sent in, because some might get lost and some might get resent. You have a checksum. That means if you calculate some magical thing, checksum 8, but one tiny word gets changed from more B to more bid, and you compute the checksum again, the computed checksum won't match the checksum in the header, and you'll know that the data is corrupted and you'll want to ask for it to be resent. It's a sum generated by performing some kind of function on all of the bytes to check that it's not been corrupted. You also have a type of packet, as in, is it video or text? And if it's video, do we need it in real time, or is it a lower priority? So if it's on Zoom or something and it's a live stream, you probably have a low time to live. It's only relevant for the next 30 seconds. However, if you're downloading a PowerPoint file, you're going to want it to last a lot longer. So that, let's move on. Sorry, I got this got confused. Your job, please. You've got P3 open. Sorry, sir. I'll be right with you. Can you work out 3 different protocols that might appear in the packet header? All of that information is on here. I've given you some examples of what goes where. Everything's on there. Okay, so let's have a look at some answers here. We've said sender and destination IP address. The type of the protocol. Remember, the protocol is a set of rules for communication. And we can have different protocols, like ones for accessing the internet, ones for sending emails, ones for receiving emails, and ones for transferring files. Any of those would be determined, would be stated in the header. the length of packet in bytes, so you know how much data it's going to be in there, and the order that's being sent. And then you often have that checksum and just some data to say, right, that's it, there's no more there. So more interestingly, let's have a look and see if you got the order right. You start the process by saying, I want to download some music. Then your web browser sends a request via the internet to the server storing the video. So that might be YouTube. Google Chrome sends a HTTPS request to YouTube saying, I want it, please. Then YouTube receives that request. It receives those packets saying, Mr. Dring wants to watch this video. The video itself is going to be not sent in one go because it's a large video. So the first part of the video would be sent in the first packet. So the video has to be broken up into smaller packets. Each of those small parts needs to have a header and a footer. So you add in everything into that header, including the sender's IP address, which would be Google's, the recipient's IP address, which is mine. The data itself would go in the main part of the packet. You'd compute a checksum to work out if anything had been corrupted, etc., etc. Then each of those packets gets sent across the internet. They'd get routed. Some of them will arrive, some of them won't arrive. They might arrive in a different order. When they do arrive, your browser then gets those packets in the right order because Windows, the networking protocol stack, has reassembled them in order for you. So the browser just sees the whole thing all reassembled. This is important. If anything goes missing, then it's automatically requested to be resent. So let's have a quick look through. I'm not going to go through that one actually. What I would like to do is this one. So we're going to draw some coloured lines here and talk through how this works. So activity 4 is the one to zone in to if you want some help with this. I would recommend going insert and shapes, and which one is best? Probably the freeform shape. And let's start with two machines on LAN E. So local area network E. That means two of these computers sending a message to each other. So I'm going to click and click. Now these computers are not directly connected to each other. So the first computer sends a message down the cable connected to its router. The router will then inspect that packet. It will look at the IP address of the sender and the IP address of the recipient, and it will say, hang on a second, that recipient is on the same network and it's connected to me. So that data is sent through the right port on the router to where it needs to get to. And I'm going to make that style nice and thick in a particular color so we can see it. There we go. Notice that the router is intelligent enough to inspect the source and the destination IP addresses, so it doesn't have to go all the way across the internet. It's fast. And that color that we used there, I would like as a I can't remember what you call it. A key, that's the word I'm looking for. So I can see that that one is that one. This time, LAN A and LAN B, local area network connected to another local area network in a different local area, would make it a wide area network. So, oops, didn't mean to do that, sorry. Insert shapes, freeform. Let's say it's this computer. It sends a message. It's only connected to its router. The router is the box with lots of network cables in. This time, the router has a routing table in software that inspects the recipient address and the sender address, and it works out that, well, it doesn't recognize the recipient address, as in the address label it's supposed to go to. And if that's the case, it forwards it up to its router. Now this router is aware of the IP address range of all of the computers on LAN A, and it's also aware that it's got LAN B connected to it too. So rather than forwarding it on to the rest of the internet, it has received some traffic from these computers, so storing a list of all of the data that it recognizes from each of the connected ports, it knows to send it through this way. This router looks at the destination address and says, well, it's not that one, it's that one, so I'll send it through that network port. So what is a router? It's just a network connected device with lots and lots of network connections, with some software that keeps track of the IP addresses of each computer connected to each network port. So these routers, oops, don't want to fill it on the outline to be a different color. These routers are not artificially intelligent, but they're more intelligent than like a hub or a switch. A hub, whenever it gets any traffic, will just forward that traffic to every other network connection on it. A router is more intelligent. It inspects the source address and the destination address, and it only sends the data to the right recognized direction. Let's see if I've got that right. Yeah, nice. I'm not going to draw this one, but hopefully we'll see sense of it. A machine on LAN C with LAN E. LAN C sends it to its router. Its router doesn't recognize LAN E, so it forwards it up. This router doesn't recognize LAN E, so it forwards it up. This router doesn't recognize LAN E, so it forwards it up. This router will have hopefully received some traffic from LAN E, in which case it can send it here. But if LAN E has never ever sent any traffic, this router wouldn't be aware of it, and it just keeps on forwarding it up until it gets to a router that has previously communicated with LAN E. So in this case, LAN E must have sent something. This router would keep track of the fact that LAN E is connected, and it routes it on. The beauty of this way of connecting stuff is that these routing tables are dynamically updating. So if you unplug this router and plug that one in over there, your network will probably slow to a crawl for a little while, and then it will self-heal. The routing tables will adapt, and it will be able to forward traffic in the right way. If you have an additional cable from LAN E straight into this router, then the data won't need to go the long way around anymore. The routing table would adapt and keep track of the fact that LAN E is connected in here, and it would find a faster way. The internet was developed to be able to survive a nuclear attack on military equipment. So if one router gets destroyed, it will not affect the rest of the internet. So that's what we're working on here. Okay, when you have done all that you can, we need to save this and submit it onto the VLE onto half term 7 networking 2, I think it is, but we've still got plenty of time to finish this off, this lesson.